Welcome back, everybody. So now we are going to hopefully relax a bit and go back to a practical lecture on SQL, because probably you know, a lot of brains fried in the theoretical lecture, because there was a lot of formalism, of heavy material. So we saw that we can take relational tables as sets of maps, and then we can do selection, projection, renaming, grouping, sorting, joins, Cartesian products, theta joins, and so on. So there's a lot of things that we can do. We saw that we can use Greek letters to represent them. And then, just like you can write arithmetic formulas like 2 + 3 × 5, blah, 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 you can also write complicated formulas for relational tables, like sigma of pi of sigma of R joined with the Cartesian product of the grouping of table C based on columns A and B, followed by an extended projection and a duplicate elimination, followed by a union. So you see, you can write very complex formulas involving relational tables and just make them, you know, flow around and be transformed into relational tables. And then one of the valuable insights that we had is that if we define relational tables as sets of maps, then we can change sets to bags or to lists in a way that is not very, let's say, that makes it easy, right? Or you just need to slightly adjust all of the operators to make them work on bags and lists. But as we saw, it's a relatively easy thing to do. All right, so we looked at the model. We know what a relational table is. We defined in SQL tables, so we can create tables, we can drop tables, we can rename tables, we can add columns to an existing tables, remove columns, rename columns. So all of that we saw how to do with SQL. So you can define schemas. The thing that we haven't really done is functionality at the level of a record. So we still inserted records and deleted records and updated records. Queried records is something we haven't done yet. This is the part that is missing, right? So today, in this lecture,
there's a question on Zoom that's kind of somewhere between the theory and the practice, which is in the exercises we can define an attribute as not null and unique. Does it make them sets instead of bags? And I think the intuition vaguely is the right direction, but the
intuition that there is a relationship is indeed correct. So let me take a bit of time to talk about that. So there is a link in the sense that what we want when we say that we have a set of maps or a set of records, we do not want entire records to repeat. But you can probably imagine that it's possible to have non-repeating records, but within one specific column, values can repeat. Let me give you an example. Foo1, Foo2, bar1, bar2. Do you agree that this is a set of maps? Because I didn't repeat the same map several times. Foo1, Foo2, bar1, bar2, these are 4 different maps. However, look at the first column, Foo, Foo, bar, bar. So it repeats twice. In that case, that would not be a unique, right? If you try to enforce a unique constraint on that column, that would fail. It would not allow you to populate the table like that. But if you don't, you can have foo, foo, bar, bar. It will repeat within the column, and that's fine. The same goes in the second column, 1, 2, 1, 2. So 1 is repeated twice and 2 is repeated twice. So you can absolutely have that in a relational table with the set of map semantics, that within each column you have repetitions, so the values can repeat within each column, while globally you don't repeat records. Who understands that? All right. If you want now to enforce that you have a set of maps where if you fear that you might have duplicates, which actually would be justified with PostgreSQL because it will actually let you have duplicates because it does the bags of maps. What you can do is enforce a unique over all the attributes of the tables together, right? And then you are enforcing that you don't have any that you don't have any duplicates. We will see that there is also a way to eliminate duplicates. In SQL, you can use the keyword distinct, which will kind of do that for you. It will eliminate any duplicates if they are. So basically, the answer to the question is that there is a link. Sorry, there is a link between the notion of unique within a column, but the link with sets would be that you need to say that it's unique globally across all attributes combined, but not attribute by attributes, right? Did I answer your question or anything that? Yeah, all right. All right. And that was the question you mentioned right during the break that we need to, okay, awesome. And continue, if you have any questions, you can interrupt me, of course, at any time. So today we'll focus on querying records because inserting, deleting, all that we've seen last time, 2 weeks ago, I mean. So we saw the theory of manipulating relational tables. We saw that we can union two tables, intersect two tables, subtract two tables, we can select, we can project, we can rename a relation, we can rename attributes, we can do the Cartesian product, the natural join, the theta join, which is when you have the additional subscripts with your own homemade criterion. Yeah, that's already a lot to play with, right? Beyond just the 4 arithmetic operations that you would have of numbers. Okay, so now it's a practical course. So we look into, guess what, SQL, the language, and how to use it in PostgreSQL. So remember that it's a declarative language. In SQL, you declare what you want. How it's done is basically not your problem. It's somebody else's problem. It's basically the problem of the engineers that implement PostgreSQL, which they probably did in C++ or a language like that. But you as a user don't need to worry about the how. All you need to do is connect to your Jupyter notebook, type your query and say what you want. And PostgreSQL is just going to give that to you. And everything you don't see will be some super complex optimization, like finding out the best way to execute it, but all hidden from you. All you will see is that it's fast. Okay, in general, we'll look into what happens when it's slow and how to fix it. The other aspect is that it is set-based. This is a way of saying that it manipulates entire relations with a single command. It's the idea, you know, when you have a language like C or C++ or Java, you always manipulate one value at a time, always one. Every method in Java returns one value, can be an integer or a string, can be an object, but it's always exactly one. In SQL, it's not the case. In SQL, you can return an entire table with a million records in there, and all of that as the result of one query. So this is why we say it's set-based. But of course, we'll see, you can, set-based is a generic term, but you could also kind of say back-based or list-based if you prefer. But really what is meant here is as opposed to manipulating one single value at a time. Something I already said, I think that SQL and SQL is the same thing. So I tend to say SQL. You can also say SQL if you prefer. That is all fine with me, but just know that this is exactly the same. These are not two different things. It has to do with the fact that it was coming from an older name before a trademark issue where it was actually called SQL for structured English query language. Okay, shall we get started? Yes, all right, so let's get started. Let's take the simplest query ever. You know, when you learn a new language, you like to have a hello world, right? How do you print hello world in there? So the simplest query here, it's not an imperative language. So the hello world simply means let's take a table and return it, like the identity function. So this here is how you take a table and return it. Let's say we have a table called persons. We want to return it. The SQL syntax is select star from persons, and this is going to return exactly the same thing. We will not, so typically all these tables that we create, they don't have names, right? They will be created on the fly, but these are not the tables that we created with schemas. These are just computations that we make. So this is why at the bottom here, there will never be a name in what I output. So it just takes the same attributes, the same domains, the same tuples or records, and that's it. So that's basically the identity function. All right, select star from persons. This, in fact, gives us the skeleton for our queries, because everything that we'll be doing now is extend this with more and more and more bells and whistles. Okay, now I will also try to draw a query plan for every query. A query plan is basically just a mathematical visual of the flow of data, in fact, based on the relational algebra. But this query is actually so trivial because it just returns the table as is that there is not really much to say about the query plan, right? I put an arrow because we just let the table flow unchanged, right? So this is why this looks a bit weird. But let's start doing actual things. Let's start with projections. How do we project to specific columns? So this is a reminder of the theory. We saw that we use the pi Greek letter in order to project a relational table to specific attributes, in that case, A and C. And what we get is another table where we only have the attributes A and C left, and B was just thrown away. In set semantics, we would need to eliminate duplicates because it's what I explained earlier on this unique thing, right? We might have that A, B, and C are globally unique, but A and C might not be globally unique, right? So if it's set of maps semantics, I would need to eliminate duplicates. If it bags of maps, then bags of maps, I don't need to, right? But this is the theory. All right, now here's SQL, and you will find how easy it is. Let's project this table. If you didn't recognize, these are Star Trek characters. Let's select first name and birth date, so just these two attributes from persons, and I get this. I get a relational table that doesn't have any name because it's flowing around in our memory on the fly. Two attributes, first name and birth date, the same domains, and we have, you see, James, Beverly, Spock, and the birth dates are the same. For whom is that clear? Who finds it easy? It is easy, right? Just select what you want, so the names of the columns separated by commas from persons. And you will see this here is something that you can really type in your Jupyter notebook exactly like it is, maybe adding, I think it's a %% SQL, you know, that just tells Jupyter notebook that you're writing SQL. But then you just type this, then you click on the magic button to run, and the table will just magically appear on your screen, just like that. And then you can just play with Jupyter notebook like this and writing queries and testing things, trying to break things, pushing things to their limits, and understanding the language. Okay. This is another one. And just to show you, in that case, there are no duplicates. Let's try to have duplicates. So let's say I'm projecting now on the original series column plus the birth date. So it's true or false because there's an original Star Trek series and there is then the next generation that came later, right? So this is why the true and false is. But then I, on purpose, use the same birth date. I have no idea if it's actually true. Technically, I just put it in order to get a duplicate. But basically, I just put James Kirk and Spock both born on March 22nd, 2233. So now we have a duplicate. You see, if we project on original series and birth date, then you see that the first projected record is the same here. Well, in fact, PostgreSQL is just going to return that to you. It will allow the duplicates. This is why I was saying that PostgreSQL, in fact, tends to have back semantics, right, by default. If you want to have set semantics, you can just say select distinct, and then it will throw away the duplicates, right? For whom is that clear? Okay. But it's really, I mean, it sounds like English, right? This is why it's called structured English query language. Okay. Okay, and then the query plan would basically just be that you take the table by from, you just, you know, read it from the disk, and then you apply pi to project to the attributes that you want, right? So this is, if I draw it now in a formal way, this is just the application of the pi operation. Okay. Now, something might have been disturbing you, and it disturbs me too, but this is how it is. It is that we are projecting, but we are projecting this after a keyword called select. Go figure. It's not actually a selection, but we'll soon see how the selection works. But anyway, as a Eselsbrücke, select is not a selection. What you put after that is the projection. Do we have a question on Zoom?
Distinct would only work for the column. Sorry, distinct would only work for the column, right? Right before it. I need to parse this first. Distinct would only work for the column right before it has been added, isn't it?
Oh, that's a good question. Meaning column by column or globally? I actually don't remember. Let's try and figure it out offline. Or maybe you can even do it during the lecture if you have an open workbook. So I think the question is, does it only apply to original series or do you know the answer?
As in for original series and not by birthday or globally. Yeah, I need to check.
Yeah, so let's check. I thought it was globally. I mean, I might not say it was globally, but let's check if it's really globally or just for original series. Yeah, so you think that it should be original series. It might be. So let's do that, and then we'll come back to you and let you know what came out of that. Yeah, thank you for this. Okay, so selection. Sorry, select keywords, but using pi because we do a projection, right? So this is just a visual. Okay, I'm not going right away to the selection. Let's rename things instead, because this is also quite easy to do. How do we rename columns? That's also, that's the row operator where we say we replace A with D, and then we get this table on the right, right? Okay, now let's try to rename columns in here. This is how you do it. You use as. So select first name and birth date, right, the two, but then you add as who and as when. So here we are renaming first name to who and birth date to when, and this is what we get. So you see, now the attributes are different, and this is thanks to that keyword as. So on the left, you have the original attribute name, first name and birth date, and here you have the renaming. Of course, you could decide to only rename one column and not the other, right? But this is how you rename. Now also a word of warning, because of course you can break stuff, right? So typically this is what quality engineers do. You try all the possible things that can break the system. Then you could ask yourself, okay, let's try to be evil and let's try to rename several attributes to the same. Well, PostgreSQL is going to be evil too, because it's actually not even going to complain. And in fact, it's going to start doing weird things. I tried it out. In fact, it's going to even, make these two columns, which already breaks the idea that these are maps, in fact. And plus, it's even using the same data here and here. What is the lesson that we learn here? Don't even try to understand what it does, just don't do it. That's the lesson. Do not ever try to rename several columns to the same. You're basically off limits of what a relational database systems should be used for, right? I have absolutely no idea why they are not throwing any error. That's just the decision they made, but just do not do it, and that's it. When something starts being fishy, you're losing your energy if you try to figure out why it's behaving the way that it does. Just don't do it. Yeah. Okay, that was just a warning because some of you might run into this. All right, now if you draw the query plan, what we did here was that you can draw a row. So here it would be a pi followed by a row. Okay, selection. Let's go to the next one. Okay, selection was the sigma symbol. We can select some of the records in a relational table based on some predicates. The predicate can be anything you want. It's just a mathematical formula that says yes or no. So in that case, the yes, no is B smaller or equal to 2. So in that case, you keep the first two because the answer is yes, and you throw away those for whom the answer is no. So let's do it in SQL now. In SQL, we are going to use a new clause. So we had select and from. Now we are going to add where. Select star. So star, remember, means we keep all the columns. So in that case, we just don't project anything. From persons, that's the name of the table, where last name is equal to crusher, and this is what we get. So we get a relational table, no name, again, it's on the fly, the same attributes, the same domains, but we only kept the one record that matches the predicate in the where clause, where last name equals to crusher. So again, select actually does a projection, where actually does a selection, right? So this is just the one thing that might be confusing, but the selection is done in the where clause. But normally it should be natural because it's quite natural to say it in English, right? Select everything from persons where the last name is Crusher. It almost sounds like plain English, right? So that should be natural. Okay, now a bit of terminology. This is called a query, a SQL query in that case. These are called clauses. The select clause, the from clause, and the where clause, right? We call them clauses. We'll get to know plenty more clauses. There are more than just select from where, but we'll see others. These are called clauses. So a query is just a series of clauses, generally a table query. This here is called the predicates. It's just the fancy term that mathematicians have for something that says yes or no. That is some question. And these are expressions, but we'll see how we actually build them. Are there any questions so far? Who is following? Okay, most of you. Okay, it's easier, right? Because now we're just looking at SQL and using intuitive queries. Okay, so now I would like to take a few minutes to show you what you can have in the predicates, because here it's a simple one with just equal, right? Earlier, the b smaller than equal to 2 is also a simple one with just an inequality, right? But what can we put in there in this where clause? So here it's again like a restaurant menu, but it's a restaurant menu that should be much, much simpler than the relational algebra, because here we work with single values. So it makes it much, much, much easier. So of course you can use parentheses all you want, but this is the way you use them in arithmetics as well. You can use or. Maybe you want to test select blah, blah, blah from where A is equal to B, or C is greater than 2, or D is greater than 1, right? So you can use the keyword or in order to do what's called the disjunction. You can use and. You can say select where A equals 2 and B is smaller than 1 and C is greater than 2, right? So this is called the conjunction. Of course, you can use the two together. You can use or and at the same time, and you can use parentheses in order to make it unambiguous. You can also use not. You can say select blah, 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 where not A is equal to 2, or where not A equal to 2, or you can combine. So or and not are the three magic keywords of logic, right? If you want to manipulate truth values, true and false. Okay, then you can compare things in there. Okay, now a word also of warning is that who knows about Boolean logic? Some of you, right? You know that it's true and false. But in PostgreSQL and SQL in general, it's actually what we call three-valued logic, not two-valued logic. What that means is that there is a third value that is unknown. It basically means you don't know if it's true or false. Why can it happen? Well, it can happen because you have nulls in your table. So if you ask if B is equal to 2 and B is in fact null, then you don't know if it's equal to 2 or not, right? Because you don't have it, it's null. So this is why we have this unknown. And here, the truth table needs to be a bit extended to make it work with unknown. So in that case, it's the truth table for or. It's common sense. For example, what is unknown or true? Well, if you say, and I don't know what, or true, it's always going to be true. True or true is true, and false or true is also true. So you don't actually care what there is on the left when you have or true. So this is why unknown or true is always true, right? But if you say unknown or false, then it's still unknown. You don't know. It could be true, but true or false, then it's true. Or it could be false, but false and false, that's false. So then you don't know. So this is why unknown or false is unknown, and unknown or unknown is also unknown. For whom does that make sense? Right? This is called three-valued logic. Okay? So two-valued would be just true and false, and three-valued is with the third possible value, unknown. The same goes for not. So not true is false, not false is true, and not unknown is unknown, right? It turns out that SQL gives you a way, if you really want to know if something is really unknown or if it's false but not unknown, you can test for is true, is not true, is false, is not false, is unknown, is not unknown. And what's going to happen here is that is true is only going to say yes if it's true, but not if it's false and not if it's unknown. Is not true is going to say yes if it's false or unknown, and it's going to say no if it's true. Is unknown will say yes if it is a value unknown and no if it is true or false. Okay? So this is also quite handy if you are so picky that you want to even test on the three-valued logic. Is it true, is it false, or is it unknown? So this can be quite useful. All right. Now let's look at the comparisons. What if we want to compare that a column is equal or larger or smaller than another? Well, here it's quite intuitive. You have the equal sign. Then you have, so this let's start with the easy ones. So this test for equality, this test for smaller than, greater than. If you want smaller or equal, then just put a smaller than followed by an equal. It's the same in many programming languages, actually, in that way. Greater than or equal than just the two signs. Difference, there are several conventions, in fact, in practice. So I think the most commonly used is this that actually means difference. So smaller than, greater than means difference. There is, in some programming languages, exclamation mark equal that is used for difference. It might be that some implementations of SQL, even maybe PostgreSQL, I don't know if it would actually accept exclamation mark equal. But typically, what a lot of people use is this one. Okay, so this is how you compare. What do you compare? Well, you can compare an attribute to some fixed value. You can also compare an attribute to another attribute, right? A equals B, right? So this is the sort of things you can do. So you can do these comparisons, and then you can use or, and, not, and combine them in any way you want, and even is true, is false, is unknown, and so on to test for three-valued logic. Okay, so this now to show you when a noun can pop up. If you say null equals foobar, so imagine you have a column called that has a value of null. Is it equal to foobar? That's going to return unknown. This is going to return unknown too. You don't know if it's different. You don't have it. Is null greater than 4? You don't know. It's also unknown. Null equals to null is also unknown, right? So this is how you can get this unknown. If you don't have nulls anywhere, then it's always going to be true or false, right? But if you have nulls, beware, this is where you can get unknown values in your Boolean computations. So this is something to keep in mind because it can get a bit tricky. Okay. You can even test for null, but then it wouldn't be with a Boolean expression, that would be with an actual attribute. So you can test for A is null, B is not null. So you can, that way, if you want to eliminate the nulls, let's say you want to get rid of all the nulls, then you can say select blah, 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 where A is not null. And then you're throwing away the records in A in which A is null, right? Okay. Do not use equals nulls. That's the message here. If you say equals null, it's going to say unknown. Okay. You can also avoid unknown by using is not distinct from instead of the equal sign. If you say is not distinct from, this is treating null like any other value, right? So this is also a trick. So you see you have a full menu to pick from. Then we have math. You can do addition, so A plus B, A times C, and so on. So addition, subtraction, multiplication, division. Modulo is done with the percent sign. You can also exponentiate with this little, I think it's called the caret symbol, where you can do powers, A to the power of B. And here I find this very fancy, actually. So you can do square roots. Actually, if you think hard, you can actually recognize some sort of square root symbol in there. But this is the vertical bar followed by a slash is a square root. The cubic root is a double vertical bar with a slash. The factorial is the exclamation mark that would be after the number to take the factorial of, or double exclamation mark before the prefix. At is the absolute value. So actually, this is already advanced. I mean, I don't even think I know that by heart. The cubic roots and so on. What I want to show you here is that there is a very powerful list of things you can do. It's like a restaurant menu where you can get very fancy things, right? So you can get square root, cubic root, factorial. You even have, this would be for maybe the geeks of logic. You can do fancy things directly on bits, but again, don't worry too much about that. This is really way beyond what I want to cover in that lecture, right? You can have cosine, sine, tangents, and so on. And so all the trigonometry, it's all in there as well, right? So plenty of mathematical functions. Okay. I hope I didn't scare you too much throwing all of that at you, right? So all I did was show you the entire menu of everything you can have in the where clause, right? I just show you all these things so you can compare things. You can use and or not. You can do addition, multiplication, division, modulo, trigonometry, exponentials, square roots, and so on. You have to be careful about 3-valued Boolean logic, because if you have nulls and you compare them to things, then you might have unknown as a value. And I even showed you a few tricks. If you are very scared of finding unknown on the way, then you can use these alternate methods for comparing stuff in order to avoid producing any unknown values. Okay. Who is following? Okay. So then if I draw the query plan or select from where query, we take a table, then we select the records that match the predicate that we've built with our restaurant menu of all the things we can have. And then we project to the columns that are after the select keyword. And potentially we rename if we use the as keyword. Okay, so that's, you see, we start having fancy query plans in there. I can also draw it like that, like this is the way mathematicians or maybe theoretical computer scientists like to draw things. Okay, now a little break to show you the sort of things that you are expected to be able to do at that point and also in the exercises. There are 4 different ways to express a query, and you need to train yourself to fluently go from one to the other. One way is plain English. Look for the first and last names of all people aged 65 and more, for example, for AHAFA. Relational algebra, all these Greek symbols and subscripts and so on and so on. Or the query plan, this is where you draw, you know, these arrows that show the data flow, or SQL. So typical things that you need to do is you're given instructions in English, please write the SQL query that does it. Or you might be given the SQL query and you're asked, please write the corresponding relational algebra formula, right? Or you're given a SQL query and you ask, okay, please draw the query plan, right? Or you're given, I don't know, the relational algebra and you ask, okay, please explain in English what it does. So you see, you need to really be able to freely move around these 4 and be able to translate from one universe to another universe. Okay, so this is as a very general explanation of what we expect from you. This is what we expect from you, right? To be fluent at walking around in these 4 realms. Okay, so select from where? Should we continue? Okay, let's order things now. Let's sort things. I have good news is that PostgreSQL also supports lists of maps. So if you want to actually sort your records, you can actually do it. It's going to be a new clause. So normally order doesn't matter, but we saw that because in practice, some people might want to sort things, you can actually do it in a spreadsheet as well. In Excel, you can sort your values. So we go to list of maps semantics. So let's use an order by. Select star from persons, that would be returning that table, but I add order by birth date. So now we are ordering the tuples by increasing, that's the default, by ascending or increasing value of the birth date, right? So the older people first and the younger people next. Okay? So by default, it's ascending, right? If you want to be explicit, you can add ask for ascending, but anyway, that's the default. So this is what it does. If you want on the opposite to be descending, then just write desk, and then it's going to do it the other way around. Who already ordered things in a spreadsheet? You know how to do it, right? Basically, you have to select the entire table, then you click on filter, activate the filter, and then if you click on one of the attributes of the columns, you can actually select sort ascending or sort descending, right? So this is how you have 2 buttons, right? To say ascending, descending. Well, in SQL, it's ask or it's desk. Okay. Okay. Now you're going to think, okay, these nulls and these unknowns, they're always in the way. Like every time we do something, we have to think of the nulls, right? And so, of course, if you order and there are no nulls, then it's easy. But what happens if you are sorting by a column and there are nulls in there? So the idea is that by default, we consider that nulls are always bigger than anything else. So they come last, right? But you can change that and say, okay, no, I want my nulls first, right? So in that case, you say order by last name, nulls first. And then, for example, if you here we had a null for Mr. Spock, right? So then it's going to come first. If you didn't write that, it would be last at the end. Okay, so this is to control the behavior of the nulls. Okay, and nulls last, that would be actually the default for ascending, would put it at the end right there. Okay, so by default, now I'm showing to you the default behavior if you don't say anything. If you don't say anything, it's going to be an ascending order and it's going to put the nulls at the end. If you say ask, then it's going to do ask, of course, putting the nulls at the end. If you say desk, be careful, I told you by default, null is always greater than anything else. So if you say desk, by default, it's going to put the nulls first, right? Because by default, nulls are bigger than anything else. So desk means nulls first, and yeah, that's pretty much it. And of course, you can override that with desk nulls last if you prefer. Okay, so you can control two things in order by. You can control ascending or descending, and you can control where on earth do I put the nulls, right? First or last. Okay. Now, just like the where clause, you can actually do fancy things in the order by clause, and you can also use all kinds of things. For example, you could say order by A+2, right? It doesn't have to be just a column name. What is these things? It's actually a string, excuse me, it's a string concatenation. So that would just concatenate the first name and the last name, right? So this is actually what it would sort on, right? So here, Beverly Crusher concatenates these two things. Beverly Crusher, James Curse, and null, because if you concatenating null with something gives you null. Nulls are always in the way, right? So order by first name concatenated last name, this is what it sorts on. B comes first, then J, and nulls always the greater. So this is the order in which we have things. Okay. I don't think people do that very often, though. I mean, most of the time when you use order by, it's just going to be one or several attributes, and that's it, right? But if you want, then you can do more fancy things. Okay. Now, let's add yet another clause. It's actually a super useful clause. Super useful clause. You will love that if you have too much data that it doesn't fit on the screen. You can limit the number of records that are printing on your screen. In that case, let's say I want to sort my table, but I only want to do the first, to see the first two. So I just add my limit 2 in there, and oh, let me use the trick. It's really an awesome trick, actually, when you explain that to me. So I need to click here, open the chat, and close the chat, and there you go. So now I ordered by birth date. But see, I only have 2 records here, the first 2. The rest, I dropped. It's not there anymore. Limits 2. This is what it does, right? In fact, when you do a search on the internet, right, with a search engine like Google, Bing, DuckDuckGo, or whatever you're using, it's actually doing a limit 10 by default, right? You only get the top 10 results. This is a limit 10 that's actually happening under the hood. Okay, and is there a question?
Can you please explain once how slide 97 works?
To see the number.
Previous slide.
This is 90.
Yeah,
oh, this one, yeah. Oh, yeah. So you need to look at on the left. So this is what you need to look at. What it's doing is that for every record in there, it's computing this thing here. It's appending the first name and the last name, and it's just computing it on the side. And then what it does is that it's going to sort the records using this as the sorting criteria. But then it throws it away because this is only done for the purpose of sorting. Does it help?
What if there are 2 same first names Does it order by the last name?
Yes, exactly. That's what actually now I realize, of course, since the first names are all different, actually it doesn't even change anything that I put that, right? That was just an example. But yes, indeed, what's going to happen is that if you have twice the same first name, then since it's ordered alphabetically, it's like in a dictionary, then this compares equal all the way, and then you start comparing on the last name. Yeah. Yeah, awesome. Okay. Now comes offset. What does it mean? It means that you limit to 2, but you skip the first one. So it means that instead of displaying the first and the second one, it's going to throw away the first one and showing instead the second and the third, right? There is a name for that. In fact, it's called pagination. This is what happens. So if you use your search engine, then you have limit 10. What if you click on next at the end? It's going to do limit 10 offset 10. What if you click again? It's going to do limit 10 offset 20. So it's to create pages of results technically. It's very useful for pages of results if you display them on a web page. So if you say offset 1, it throws away the first one and then returns the 2 that come after that. So this is what happens. In that case, we throw away what would have been the first birth date, that would have been Spock, and we display the next 2, which is James Kirk and Beverly Crusher. All right? Does it make sense? For whom does that make sense? Okay. Again, the best way to understand limit and offset, think of your search engine where you click next 10, next 10, next 10. It's limit 10 offset 10, limit 10 offset 20, limit 10 offset 30, and so on and so on. Okay. And this is actually going to be very useful to you if you are querying enormous amounts of data and you just want to peek at the first 5 or the first 10, and you add this limit 5, you will get quicker a view of the first 5 than if you try to print the entire table. So limit is super useful in practice. Okay. By default, if you don't say anything, then it's not going to limit anything. It's just going to do limit all. So it doesn't put any limit, and offset 0, meaning that it doesn't throw anything at the first, right? So limit all, offset 0. Okay. Now, again, a word of warning about the don't ever do that. What if we try to put limit 2 and offset 3, but without an order by? Well, I have no idea what's going to happen. The reason is, if you don't use order by, PostgreSQL doesn't guarantee any order. It's in the bags of set semantics. It's only caring about the order if you use order by. So if you don't order by anything, basically, PostgreSQL has the total freedom of doing whatever it wants with the order. It's whatever makes your query faster. So if you try to do limit 2 offset 3, it will throw at you 2 of the records, but it can be any of them. It's almost a random draw, right? So this is why you should never, ever, ever use limit and offset without order by. It's a very bad idea. Always with order by. Do we have a question?
Could you explain what would happen in the previous example if we wrote offset 2, just to understand it better?
Sorry, I didn't get that.
So what happens if, I think in this example, the offset was 2 instead of 1?
I think then it would only return 1 record because there is no 4th record, right? And then if you grow, then there will be nothing left, so it will be empty. Okay. So, yes, exactly. Is it the last one, James? Or is it Spock? No, Spock is the last, isn't it? 20. No, sorry. Yes, you're right. 22, 23. Well, it's in the 23rd century, so I'm not used to comparing birthdays. So yes, James comes last. So yes, that would be James Kirk alone. Yeah. Okay. Awesome. Okay, now this is a summary slide. I want to show to you everything we've learned so far, all the clauses. So it's actually easy because it always comes in that order. Select from where order by limit offsets. which concludes today's lecture, and we'll add more clauses next week. So thank you very much, and I'll see you next week at 10 again.